Hello, everyone. I'm sorry this took me so long. I have had some technical difficulties this morning. Let's see. Okay, I can see there are about 15 of you. There we go. Oops. Let me. Okay, I think I've almost got all of you admitted here. There we go. All right. So I'm sorry this took me so long. I was having technical difficulties this morning. I think my computer crashed overnight, so I apologize for this taking so long to get started. I am going to, let's see, how am I going to do this? I'm going to put this as a grid. There we go. That makes it easier for me. Okay. I'm going to go ahead and get started with the colligative properties, but before I do, first of all, if you guys have questions, pop it up in a chat if you have something. It doesn't have to be about what we're doing right now. It can be about assignments or, you know, what you're supposed to do about something. I did want to remind you that if you're having trouble printing out the Rocketbook pages, you don't have a printer or you don't have ink or whatever the case may be, just send me your mailing address and I'm going to be mailing out some of those to some people this morning so that you can have some Rocketbook pages to submit things with. So just send it via email and I will get those out as soon as I can. I have most but not all of the exam twos scanned and sent out to people. So if you haven't gotten it yet, you should be getting it this afternoon. And you have at least until the end of March to do any exam corrections. And I'll try and get those along with the exam one corrections into the grade book so that you guys can see it. All right, so let's see. On Connect, it had originally said that homework 10 was due last night, and then Canvas had a different date, and that's because when I originally set it up, I was thinking we were going to be starting classes on Wednesday, not Friday. So the Canvas dates were correct. Homework 9 was due last night. Homework 10 is due on Tuesday. So it's fine if you turn in homework 10 even tomorrow, and I'm not going to be worried too much about things being a little bit late as it is. Homework 10, if you looked at it, you probably were like, we haven't gone over this yet. So that's perfectly fine. Okay, any other questions before I get started? Okay, so I'm gonna go to my PowerPoint. And okay, so we're going to start talking about colligative properties today. Let me pop this up. Remember, our colligative properties are, oh, I should have scrolled down to the appropriate place. Let me escape out of this. Remember, these are the ones that are only affected by what the concentration is, not by what the identity of the solute is. So if I have a 1 molar solution, it doesn't really matter what the 1 molar solution is, whether it's salt or sugar or whatever, it's just the number of dissolved particles. The only thing that matters is that when I have an ionic compound, I have to count the ions separately. And these include vapor pressure, boiling point, melting point, and osmotic pressure. For vapor pressure and osmotic pressure, you just kind of need to know what it does. We're not going to do any calculations. Boiling point and melting point, that's what we're going to do today, is go through some calculations on that. We looked at this slide last time where we showed how these things were connected. Since the vapor pressure is decreased by adding a solute, and that's because there's fewer solvent particles at the surface, that's going to make our boiling point higher because it takes more energy to get to that higher boiling point. But it also has, as you look at this curve, the opposite effect for the freezing point. The freezing point is going to go down. So that's 3 of our properties right in here. And we'll talk about osmotic pressure in a minute. Okay, each substance is going to have its own KB or KF. Those are the boiling point and freezing point constants. So this is how much the temperature is affected by having a solute or solvent present. Having a solute present. And I will always provide these for you. You're never going to have to guess at what those are or memorize them. Okay, so let's say we have a solution of acetic acid, and I need to move this screen so that I can see. Acetic acid that is 0.020, and then I've got a lowercase m. Remember that lowercase m means molal, which is moles per kilogram of solvent, in this case acetic acid. And so it is 0.020 molal in potassium chloride. So things we need to be paying attention to are that this is an ionic compound, and we know that because there's a metal and a non-metal. And so that's going to give us a Van Hoff factor of 2 because it's going to break up into 2 ions. And then we also have our concentration, and then we're going to need to know the KB for the, advance there, for the acetic acid. So this is the formula we're going to use, and it's going to look almost identical for freezing point, except for these will be Fs. So the delta T is how much it changes. It's not our final temperature, it's just how much it changes. The I is our Van Hoff factor, so that's 2 in this case. KB we have to look up on a chart, and the molality is this here, okay? So we don't have to change this number to plug in here because we're going to be changing the I from 1 to 2. All right, oops, I didn't do, oh, yes, there it is. Okay, so KB is 3.07. This I would just look up on a chart here. I wouldn't have that memorized, don't have a way of figuring that out other than just looking it up. My molality is 0.020, my I is 2, so I just plug it in here. So whether it's right now or sometime later, go back to these slides, make sure that when you plug these things in that you can see what the how to do these calculations, and you can get them the same way. And so what we'll see is that our change in boiling point is 0.12 degrees Celsius. Now that's the change, that's not the final boiling point. So we have to know the original boiling point of acetic acid to know what the final boiling point is. Oops. Go back to my slide. So if I go up here, acetic acid normally has a boiling point of 117.9. And so then when I do, oops, where is it here? This calculation, it's changing by 0.12. So I'm just a little bit over 118 when I'm doing this calculation. So you can see that in this case, it doesn't change a whole lot. All right, so that kind of brings us to the next one with salt and water. Now, before I go on to the next one, does anybody have any questions about how we did that last calculation? Okay, so why do we add salt in water when we are boiling something? So a lot of times people will say, oh, it's because it raises the boiling point. So we're going to look at how much the boiling point of water is going to be raised by adding salt to it. Now think about how much water 1 liter of water is. This is like a 32-ounce drink, so a pretty large sippy cup from McDonald's or wherever, big gulp cup, but it's not a whole lot of water to be boiling something in. When we add the salt to it, we want to see how much salt we have to add to raise that temperature just by 3 degrees. So from 100 degrees to 103 degrees. So same formula here, delta TB is equal to IKBM. Now, in this case, KB is going to be a different number. Last time it was 3 point something, and because we were working with acetic acid, but this time we're working with water, and so it's going to be a different number. So waters, if we look it up on the chart, is going to be 0.512. So I would just get that number by looking at the chart. Why is it that I have the 2 here? Think about that for a second. So remember that I am, hang on just a second, chat. Okay, where does I come from? I is the number of particles that something dissolves into. So if I have an ionic compound, it's going to be the soluble ions, as Clay says here. So if I have potassium chloride or sodium chloride, there are 2 different ions present in that one formula. And so that would be an Van Hoff factor of 2. But if I have something like sugar, sugar is covalent, so it just dissolves as one whole molecule. So if there's no metal present, we're going to assume a Van Hoff factor or an I equal to 1. If there are metals, that's when we start dividing it up into separate ions. All right, so for sodium chloride, it's going to be 2. Okay, so I've got everything plugged in here except for this M. And notice that this M is both the symbol for the molality and also used as the unit of molality. So that can be a little bit confusing sometimes when you're looking at it. All right, so I plug this in, solve M, and I end up with 2.93 moles. Well, that doesn't make a lot of sense to me when I'm trying to figure out how much is there. So if I'm trying to figure out how much salt I have, I need to convert that to grams. So 171 grams of sodium chloride. 171 grams. Now remember that a gram is about the weight of a paper clip or a raisin. So if I have 170 of these, that's an awful lot of salt to be dissolving in 1 liter of water. So when we add a little bit of salt to something, we're making spaghetti, we're boiling water to boil eggs, that's not really going to affect the boiling point a whole lot because we'd have to have a ton of salt in order to make that difference. What it does do is it gives gas molecules a place to start forming. So those little particles help the boiling to get started once it's at the right temperature. Instead of having the flat surface of the pan, it has those little rough edges to start boiling at. But the temperature is still going to be. All right, so before we go on to freezing point depression, any questions here? Okay, so freezing point depression is going to work pretty much the same way. I'm going to mark a couple of things down here. Okay, we have the same formula here. Now I've just got the negative in front of here to tell us that it's going down. Usually freezing point depression is listed, this AF is listed as a positive number, so we need the negative to tell us that the temperature is going down. If the K is listed as being negative to begin with, then we don't need this negative. The main thing to remember is it's called freezing point depression because it's going down. Okay, so temperature is pretty easy to measure. So in practicality, we don't usually do the calculation to find what delta T is. We find it to determine something else. In the lab that you all are doing this week, you are going to be finding the molar weight of a particular compound. So this is kind of illustrate, I think it's this one that's going to illustrate how you go about doing that. All right, so if we have 5.01 grams of known salt, so we don't know what it is, we can't look up the molar weight, and it's dissolved in 100 milliliters of water, and the freezing point of the solution is negative 2.05 degrees Celsius, we can, from this formula, determine the concentration, and then if we know the basic generic formula, we can determine what the, back too far, we can kind of determine what the molar weight is. This is telling us that we have 1 metal and 2 nonmetals. All right, so I saw there was a comment in chat. Let me see if I can find that. Where are we? Come on, give me my screen. Stop share for a second. Okay. Oh, I'm breaking up a little bit. Okay. I have my chords in here. What I'm going to do is I'm mute all of you. And I think, oops. I think that should help a little bit. Oop. Rachel's trying to get into class. Hi, Rachel. Sorry we kept you out of class for so long. Okay. Hopefully that will help keep me from breaking up so much. Okay. So let me get back to the PowerPoint. Okay, so here's our setup. We're going to try and find the molar weight, and this is because this is similar to what you'll be doing in lab this week, if you didn't hear me say that before. So we have, in this scenario, 100 milliliters of water, 5 grams of an unknown salt, and we know the freezing point depression. And then we're going to work on some partial knowledge that this somehow has the formula of 1 metal and 2 nonmetals. So what do we do with this information? All right, so the basic information is at the top of the screen. And I seem to have, oops, lost you all. So I think I'm not sharing this. Let's go back here. Screen share. Okay. Now you should be able to see it. Okay, now at the top you should see the basic information that we had from the problem. Another question in chat. Let me pull that up. Okay, now I've got the screen shared. All right. Okay, so here's our formula. Delta TF is equal to negative I KFM. So see how similar it is to our boiling point one. We just changed these numbers, and the negative just means that it's going down. So we know from our problem that the freezing point change is negative 2.05. The ion concentration is going to be the Van Hoff factor I times the concentration. And at this point, I don't know what the concentration is. So I'm going to just divide these two numbers, my change in freezing point and my temperature depression, or I'm sorry, the change in freezing point and my freezing point constant. Going to divide these two, and this gives me a concentration, 1.10 molar. This is the total ionic concentration. So what it says here, the ionic concentration. Now, if I didn't know anything about the formula, that's the best I would be able to do. But we said that the formula was mx2, which means I have 1 metal and 2 nonmetals. So then I is equal to 3. So from there, I can figure out that my formula concentration is equal to 1/3 of this 1.10. So 1.10 is equal to the Van Hoff factor I times the concentration. My Van Hoff factor is 3, so I'm going to divide 1.10 by 3, and that gives me my formula concentration of 0.368 moles per shouldn't be moles per liter, should be moles per kilogram. I'll have to change that. And so what does that tell me? Well, I didn't start off with 100 kilograms. I started off with 100 milliliters. So I'm going to have to change to the appropriate units here. So if I had 0.368 for 1 liter, that means I only had 0.0368 for 100 milliliters, okay? Because 100 milliliters is 1/10 of 1 liter. And then, and I'm making this assumption here that 100 milliliters of water is equal to 100 grams of water. So since I had this number, 0.0368 moles of my solute, my MX3, dissolved in that 100 milliliters, then that's the number of moles that were in this 5.01 grams. So my molar, or my molar weight, MW, is going to be grams per mole, the grams of the solute divided by the moles of the solute. So 5 divided by 0.0368. And so that gives me a molar weight of 136. And then I could use the periodic table or any other information that I had to try and figure out what could be something that has the formula MX2 and has the molar weight of 136. We're not going to worry about that here. So in your lab this week, you're going to do something similar. You are going to find the melting point or the freezing point of lauric acid. So it's not going to be water, it's going to be something different. Lauric acid, pure, and then when it has some benzoic acid dissolved in it, and then you're going to take that change in freezing point and use that to determine the concentration. Now the nice thing about this is since they're both organic compounds, your Van Hoff factor is 1 and you don't have to worry about it. You just have the KF and the molality. So those are just the 2 things that you worry about there. All right, so I'm going to pause there in case there are questions. All right. This is the kind of question that I've asked as in group work before, and I'm not going to worry about it right now, but I wanted to address this because this is the main way that we see freezing point depression. In the winter, we often use salts to de-ice the roads. So they'll just put salt on the roads. And so you might have sodium chloride is a common one, potassium chloride, magnesium chloride, calcium chloride. So think about for a minute, put in the chat window, what do you think would be the advantage of using something like magnesium chloride or calcium chloride over using something like sodium chloride or potassium chloride? Why might we choose one of these other things? All right, so Abby's joined in with a larger Van Hoff factor. Thank you, Abby. And yes, that's exactly the reason. So when if I dissolve 1 mole of magnesium chloride as opposed to 1 mole of sodium chloride, I've got more particles dissolved, and that helps to lower the freezing point even more. But that's not the only factor that we have to consider. And of course, everything in the real world when we're deciding what to do is probably going to come back to how cost effective is it. So cost is probably going to be something we consider too. So cost, how much does it weigh? So it doesn't really help us a whole lot to use something that weighs a lot more if we get more moles out of it, because then we just have to use more mass anyway. And then the Van Hoff factor is in there. So it turns out when we consider all of these factors together, usually sodium chloride is the better choice just because it's so cheap compared to all of the other ones. And then of course there's solubility. It wouldn't help us a whole lot to use aluminum oxide, even though there's lots of ions, because aluminum oxide is not soluble in water. All right, so let's just think about this for a little bit. Try this out on your own. A saturated aqueous solution of magnesium chloride, so that's a Van Hoff factor of 3, has 5.0 molal. And we want to know what is the saturated solution's freezing point. So we're going to use delta T is equal to I KFM. The KF for water is given to you right here, 1.86. And we're going to need to use I for magnesium chloride. So I'll give you all a chance to kind of chime in here. Got a couple of people have already responded, but I'll give everybody a chance to figure out which one they think it is. Got about 10 of you in there. Okay. All right, so let's see what people's choices are here. Getting a lot of D's from everybody. So yeah, the first thing to remember is that this is going to be a negative number. So we got to make sure that we're choosing the negative things. Now it works out nicely for water because its freezing point is 0. So the change is going to be equal to the freezing point, but just be really careful that when you are doing this with something other than water, that you're remembering that we're not just going to take that change, we're going to subtract it from the original one. So when we multiply these out, we have the 5.7 times the 3 because there are there's a Van Hoff factor of 3, and then we multiply that by the freezing point constant there, KF. All right, I am going to, let's see, I'm going to stop sharing this for a second and go back to this screen. Okay, so I am going to switch to the second meeting that I sent to you because I think we only have a few minutes left on this one. And that way, if people have questions at the end, we don't get cut off. So like I said, I'm not planning on going past 9:50, but I am gonna log out here and then start the other one in 2 or 3 minutes, give you a chance if you need to, go do something. If you wanna turn on your microphones and chat with each other, that's perfectly fine. Do that for a couple of minutes and then we'll start the other meeting.